Ladies and gentlemen, dear colleagues, good to see so many students coming. I'm Ion Petre, I'm a professor of complex systems at University of Turku, and I would like to welcome all of you to a new event in our Distinguished Lecture series. Our guest today is Professor Marta Kwiatkowska, a truly distinguished computer scientist with influential contributions to several areas of our field. Marta Kwiatkowska is a professor of computing systems and a fellow of Trinity College at University of Oxford. She is a fellow of ACM and a member of Academia Europaea. Professor Kwiatkowska has made fundamental contributions to the theory and practice of model checking for probabilistic systems, focusing on automated techniques for verification and synthesis from quantitative specifications. She led the development of the PRISM model checker, the leading software tool in the area and the winner of the HVC Award 2016. Probabilistic model checking has been adopted in diverse fields, including distributed computing, wireless networks, security, robotics, healthcare, systems biology, DNA computing, and nanotechnology, with genuine flaws found and corrected in real-world protocols. Professor Kwiatkowska was awarded an honorary doctorate from KTH Royal Institute of Technology in Stockholm in 2014. In 2016, she was named an ACM Fellow, recognized for advances that are transforming science and society, I quote, for contributions to the theory and practice of probabilistic verification. In 2017, she was named an EATCS Fellow, I quote, for pioneering work in the development of model checking for quantitative systems and in its application to a wide range of areas. Also for outstanding mentorship and serving as a role model for female researchers in computer science. Professor Kwiatkowska is the 2018 Milner Award medalist, a distinction awarded by the Royal Society for outstanding achievement in computer science by a European researcher, and is the first female to win the award. Her recent work has been supported by the ERC Advanced Grant Veryware and the EPSRC Program Grant on Mobile Autonomy. Thank you very much for accepting our invitation. The floor is yours.
Thank you. Good afternoon. And thank you for the invitation and a very generous introduction. And it's a great honor and a pleasure to be here in Turku to give the distinguished lecture. What I'm going to talk about is what I talked about at the Royal Society in November, and this is work which is based around the topics that I have been working on and focusing on my most recent work, and that's application to self-driving, autonomous driving. Now the talk is at a high level because it was really a public engagement event at the Royal Society. So if you are interested in seeing the formulas, you will need to look up the papers. There are links to the papers in the talk, but you would need to find the formulas and actually, the description of the approach and more details in the papers. Okay, so first of all, I wanted to start by saying that as a computer scientist, I feel that we are living in very exciting times, really very exciting times for our discipline. We know that robots are taking over the world. They are becoming members of our society. They are taking over the tedious tasks. Perhaps they can't quite do household chores, as indicated here, but they are also taking over the dangerous tasks. So the robot on the right is actually a motorcycle driving robot, which is a very good idea. You want to replace the human in a dangerous task of testing motorcycles on the road. As a computer scientist, I should say that, of course, these are robots, so they are all major engineering efforts. But of course, the brain of all these robots is a computer program. And this is all designed by computer scientists. Now, also as a computer scientist, As we know, up until now we have relied on silicon, but Moore's law is reaching its limits, and in fact it has been arguably pronounced dead by some people. So what we are looking towards is alternatives to silicon. And one alternative that I have also been involved in is DNA computing and more broadly molecular programming. And this is in fact how you can use chemistry, and chemical reactions in order to compute. Now, the nature of computation is very different in this context, because what we are talking about is computing with molecules. So you need to design a scheme which would take some molecules as inputs, and then it will process them and process them as outputs. And if it happens in a test tube, the economists called it computing with soup. Now, what's the state of the art? As of 2012, at Caltech, they have designed a DNA program that can compute a square root of a 4-bit number. And it took quite a long time. You see, we are not doing DNA computation for speed. We are doing it because it can interface with the living world. But more recently, last year, they made progress. What they can now do is AI. They have a neural network, and that neural network actually does MNIST recognition. If anyone works on MNIST, this is the handwritten digit recognition. So this is also very exciting, and I will show you what my role in this has been. If we move further, in the past, something like 20 years ago, I think all the power of computing came from the hardware companies, silicon. But these days, we have moved beyond designing hardware circuits the way that they were being designed before. They are really programmed. And in fact, what we can use is we can use adapted programming languages and techniques that were developed for programming to do verification. But more so, this is not just in the context of the digital circuits. This is also arising in the context of programmable networks. I mean, we know that networks, to start with, they were all wired. They are no longer wired. You can program the connections. So we computer scientists in this engineering world, I think our importance is rising. So chips with everything no more, but what you have with everything these days is deep learning. I think I don't need to convince you, because you see it, I think, in news feeds, etc. And it does not just deep learning, but AI in general. AIs do seem to take over and do the kind of background tasks for us. What do they do? Face recognition, Google Translate, Alexa. Anyone here doesn't have Alexa? But the greatest excitement is in self-driving. And I'm going to show you here a video. And this is a dramatized view of what life might be like in a few years. We don't know how long it's going to take us. So what you see there is you have autonomous cars and humans, and they are all perfectly coordinated. If you think about it, the communications technology is there. They can all see each other, they can communicate quickly enough, they can synchronize their moves. Right, but we are not quite there yet. So what I'm going to tell you about is where we are, what we are doing right now. And this comes from a collaborative project which I have with engineers, roboticists at Oxford, the Oxford Robotics Institute. And this is a video from the self-driving car software. If you have been to Oxford, this is Broad Street, which is just outside Trinity, entrance to Trinity College. That's my college. And what this software is doing is it takes in images and then classifies in those images cars, pedestrians, and cyclists. Okay? A very simple problem. What they are trying to do here, the reason I'm showing you day 4, is that this technology is based on experience learning. So what they do is they send these cars to drive around Broad Street to learn the fixed environment. Okay, that's the houses and roads, so that they can then in real time recognize and put these bounding boxes around cars and humans and pedestrians. Okay, so that's more or less the state of the art. I think other self-driving companies are a bit further along than this, because this is from a couple of years ago. I'm not allowed to show what they are doing right now in Oxbotica, which is the spin-off. Okay, so the challenge of autonomous driving is, of course, a huge and very complex challenge. And it is not just a challenge for computer scientists. You can see that there has to be a computer program which would actually do this, classification. But it is a complex engineering and AI problem. Now, at the heart of it is software, which is what we computer scientists do best. And inside the car, what you see is a mix of old technologies that work and also some new technologies. So, for example, control engineering and AI planning, they are all relatively well-known technologies that have been adapted to this context. But computer vision has moved on, because computer vision is now based on deep learning. And in fact, not just computer vision, a lot of control features in the cars these days in Waymo are based on deep learning. Now, deep learning is something which requires high quality data and a lot of processing power. And the reason that this deep learning is possible is because companies like NVIDIA have pivoted now, and they are developing GPUs specifically for automotive use. So this is an image of an NVIDIA GPU, which will probably be sitting inside many of your autonomous cars. Now, high quality data, now it's quite quality data. What you see there is a LiDAR image of Oxford, which comes from my collaborators. But deep learning relies on labeled data. So it's not good enough just to take a lot of images. What you also need is you need to be able to label these images to tell the deep learning training process where the car is. And there is a lot of manual effort involved. In fact, there are sort of whole companies in Africa where people can sit and painstakingly label images of urban scenes with cars and bounding boxes. Okay, so that's behind the scenes, but where we are is we are making great progress. We are really making great progress, and there is a lot of deep science involved. Okay, but would you trust a self-driving car? So how many of you would? I mean, how many of you would actually
a pedestrian or a driver.
Okay, we'll come back to that. Yeah, but no, I'll ask a specific question. So would you trust a self-driving car to take your child to school? Yeah, okay, great, okay, thanks. Maybe. Well, if you move to Arizona, Waymo, which is the Google offshoot, they've already started a program, and you can sign up. Families can sign up, and they can use these cars. This is officially for testing purposes, but they do send, school kids to clubs and various things. Yeah, so this is a fact. Now this is called the Waymo Early Riders program, but Tesla is doing something similar. Uber is also testing. I don't know about Finland, but in the UK we have 5AI, we have Spotica, which is a spin-off from my collaborators. Okay, so how many of you would definitely not trust? Okay. Well, I think you are in a minority now. I think the others probably want to see more evidence. Okay, right, but there has been unwelcome news in recent months, and what I'm showing you is two examples. So the one on the right here, this is actually a Tesla. Okay, so Tesla is an autonomous car, but what it is a car with an autonomous mode. And when you buy that car as a driver, you have to commit to being responsible for the car's actions at all times. So when you press on the autonomous drive button, you are still in control. And in fact, Tesla is supposed to remind you, so that you are aware and so that you take over control. This poor person died because the car just veered into a crash barrier. Okay, as you probably know, self-driving cars are trained to follow lanes by looking at the white lines. This was a crash barrier which went across the white lines. We don't know what happened exactly because this is a commercial secret, but there are people who are trying to make this observation in the internet. Okay? Now the other example that I'm giving you is another crash. This time is with Uber. There was a pedestrian which was killed by an Uber being test driven. So there was a test driver in the car, and the role of these drivers is to actually take over in dangerous situations. But as we know, if you've been driving, for example, your spouse is driving and you are sitting there on the motorway, you tend to doze off. So you probably don't even have to look at the phone, which is what they were trying to say. But you just don't maintain your attention on the road. Now, but that wasn't the cause of the accident. This is still a preliminary report. It's not a final report, but in a preliminary report, it was established that the learning software actually did recognize the bike, the pedestrian, recognized first an object that it didn't recognize in a couple of seconds before the crash. It did recognize it as a bike, but this was switched off for the testing to avoid erratic behavior. Okay? So what we are looking at is processes for testing of these new devices which are not necessarily safe. Of course. So I just wanted to draw your attention to this, but of course this is a hugely complex problem. It is a hugely complex problem. Imagine this situation, in real traffic. I don't know. I suppose in Turku. You go to some, small towns in England as well. It is very different in California, where you are on a highway and you go from A to B on a highway, and everybody drives at the same speed. This problem is then quite well understood. But if you try to take the car into these situations, then of course, how do you communicate, with the pedestrians? How do you communicate with drivers, if you have human drivers as well? The car has to recognize traffic signs, classify them. And of course, you might say, well, but we've had this problem before. It's always existed before. But no, the key here is autonomy. The key is that what is driving that car is the brain, and there is a computer program. And computer programs can have flaws in them, okay? They can go wrong. Okay. And another aspect that's driving these is trust. And I think I've already tested this on you. People are developing trust in different ways. Children are naturally very trusting, for example, of robots. But I think scientists tend to be less trusting of, these autonomous cars. Right, but this is, of course, a safety-critical problem. This is a hugely safety-critical problem. So what we do need is guarantees. And I got into this problem by actually looking at these images that I showed you from the video from the Oxford Robotics Institute. I mean, you have bounding boxes around cars, pedestrians, and cyclists. And me, as a theoretical computer scientist, is worried, but how do I know that this is definitely a car? And they are not thinking about this because they are so excited about making progress, with deep learning, that they are not thinking about it. So that's why I started working on this. And, my key point, and this is a general introduction to my research, and I will now go into a bit more about my research and other examples, and I will come back to self-driving, I promise you. So my research is about formal verification. So what I want to do is I want to take pieces of software and then establish provable guarantees. So what you have is you have some software which you can abstract into an automaton. Okay, I'm really glad I'm saying automaton in Turku. And there are also other types of automata. This is an example of a timed automaton, but of course these days what we will be abstracting things into is also deep learning networks, okay? They are built in a very different way because they are built by the learning process, but in a real system you'll have a mix of all these types, and they all need to synchronize and talk to each other. So what my work aims to do is to develop techniques for modeling, which are rigorous and mathematical, but then also come up with a proof, but that proof can be obtained by a computer program, for example, a model checker. That's the proof that the model satisfies a given specification. But more recently, what we've started working on is synthesis. So turning the verification question around. Now, in verification, it's fine if you can prove something, but if you can't, you have to fix the error. So instead of doing that, what we are asking is, can you now synthesize the software? Can you construct the software so that it automatically guarantees it? And that's why this is called correct by construction, okay, model. And my specific focus is on techniques which are algorithmic. That is, techniques that are adapted in such a way by discretization or whatever, so that you can run an algorithm in order to obtain that proof. And more specifically, almost all my work is focusing on probabilistic guarantees, because the world out there, from molecules to autonomous driving, etc., that world is very stochastic. Why? Because there is unpredictability, there is uncertainty about how, a pedestrian will behave, for example, but there is also randomization. Randomization is something that, for example, your Bluetooth phone is using when it's trying to communicate with other devices. So my work has been focused on developing models and verification techniques, but specifically for probabilistic systems. And this is most of these techniques, not all, I'll show you some of them, have been coded into the PRISM model checker, which is a probabilistic model checker, and that one will take a probabilistic program and verify whether a given specification holds for it. Okay, so if you're interested in finding out about PRISM, then I need to refer you to publications, but what the rest of the talk is going to do is to stay at a high level. I don't know how many of you have seen Monty Python. Okay, so what I'm doing with this talk is just asking the question, what have the Romans ever done for us? Except that I'm not talking about the Romans, I'm talking about probabilistic verification. So I'm going to show you a few examples of concrete lessons learned from sort of looking at an example and trying to verify it, and I will come back to self-driving. Okay, so the first example is actually Bluetooth. Okay, so I assume you all have a Bluetooth-enabled phone. But do you know that that Bluetooth-enabled phone actually uses randomization at many different levels? So if you have your Bluetooth phone, if you walk around with a Bluetooth phone, it will constantly keep looking for other devices. It will try to identify whether there are other devices in the vicinity. And this is called the device discovery protocol. It's a protocol, if you've heard also about piconets, it's up to 8, and the idea is that it needs to discover but also find a leader, a leader in the piconet, because then that leader will need to establish certain properties of the network. So when the Bluetooth protocol became popular, I had a project and we started looking at how it works and trying to verify probabilistic guarantees. Okay, so a probabilistic guarantee is, well, you might want to ask, okay, I want this process completed in 5 seconds, but if the algorithm is probabilistic, you can't. You have to say, I want high probability that this process is completed in 5 seconds. So that's what we were looking at. But then it turns out that Bluetooth protocol is based on a so-called pseudo-random frequency hopping sequence. So every device will follow a sequence of frequencies. They can only hear each other if they are physically on the same frequency. But they start with a free-running clock in a random position of that sequence. So they'll start in some random position and then they will just keep going, and only very occasionally they'll hear each other. Now, when they hear each other, then they try to establish a connection. But of course, what you do not want is want the situation, okay, I hear, let's talk, I hear, let's talk. What they do is they use randomization. So instead of saying let's talk, they will first wait a random amount of time and say let's talk. Okay? And randomization then decentralizes it and allows them to eventually communicate. They have a certain random time, then they will increase that random time. Now, what we did with this example is we were able to build a model, but because of that pseudo-random sequence, this model is absolutely huge, and it didn't fit into a single model in PRISM. It was 32 Markov chains, and as you can see, 17 billion initial states. This is because of these initial, positions. This is just for 2 devices. Okay. And two messages. But then what we were able to do is we were able to compute the worst case time, and that's 5 seconds. Not just that, we were able to pinpoint the specific positions in the initial sequence which would lead to that time. Okay? And moreover, we were also able to find a flaw in an analysis which was done using random variables. As is common with random variables, you have to make independent assumptions, because otherwise, you just don't have a closed form solution. And it turns out that that independence assumption in that case was incorrect. And what we were able to compute with PRISM is to expose that. So that's one example. Okay, another example is from a slightly different situation. This is now a real-time system. A real-time system, I mean, some people may need a pacemaker. And a pacemaker, they might need a pacemaker because their heart is not working well, and that means it does not beat regularly. The heartbeat beats at 60 to 100 beats per minute, but for some people it may just not beat. So a pacemaker is essentially a device that counts the time in between the beats, and if it takes too long, it will insert an artificial beat. Okay, it's a device which is implanted under the skin and connected directly to the heart. And as you can imagine, it is a real safety critical system. Real safety critical system. And to start with, pacemakers, this is a very old technology. They were being developed by following engineering rules and safety standards. More recently, because of course it's very easy to reprogram and improve a pacemaker, it turns out that some of these improvements were done incorrectly. And there are people who have been killed by bugs in the pacemaker, killed by code. So this is not killed by, the device, it's killed by the software in the device. So what we did is we set out to develop a modeling and a verification framework for pacemakers. So it might sound easy, okay, but all you need is a model of the heart and a model of the pacemaker. Of course, I'm not going to build a complete model of the heart. I will only focus on the electrical flows of the heart. The pacemaker, as I said, is a time system, real-time system, so I actually have a timed automaton, okay, timed with additional information, modeling the pacemaker. And for the heart, I'm not showing you, for the heart I actually need a differential equation system in order to model the electrical flow. And then what I do is, I apply verification. I have the two models, I connect them, okay? And then I'm asking a question, basic safety. Over a fixed period of time, does the heart paced by the pacemaker beat 60 to 100 beats per minute? But you can also ask more complex questions. You can ask questions about energy usage, because of course every time the pacemaker beats, it uses a certain amount of energy. You can also ask a question about cardiac output, okay? And in fact, for some people who have chronotropic deficiency, the pacemaker needs to adapt to how much or how little the person exercises. And for those people, the pacemakers are actually tested directly on humans, but with the techniques that we've developed, it is possible to learn from the ECG of the patient and then test it in silico. Okay, so what I'm going to show you is what that means on this example. So I'm showing you a healthy heart. The models are in Simulink, and a healthy heart just has this regular, beat. Now, if you have a patient who has bradycardia, bradycardia means that the heartbeat is slow, and this is potentially fatal. So it does not, beat regularly. But if I now connect it to my pacemaker, what you will see is you will see the red beats. The red beats are the artificial beats. Okay. Right, but you can imagine, these artificial beats have to be timed, but we are all different. We all have a very different characteristics in terms of the number of beats per minute. So what our question was, can we use this in order to optimize the pacemaker, both the energy of the pacemaker, but also perhaps even cardiac output? Right, but what we asked is we actually asked a synthesis question. The synthesis is assuming that I have a pacemaker timed automaton, but what I have as a variable is the length of time that I wait until I have to issue a beat. Okay? And then if you understand, the theory, you can then set up an optimization problem which would find the optimal time given the ECG of a particular patient, okay, for to wait for that specific patient until issuing a beat. And with this, we were able to obtain significant improvement over default values. So the pacemakers are all parameterized, and these parameters have default values, but when the surgeon has operated, and also sort of a few hours after the operation, these parameters are set by the patient. But we were able to improve on this using the synthesis. Now, but what you can do is you can go further. So you can, for example, explore trade-offs in optimal delay synthesis, because there are trade-offs. I might want to optimize energy usage, but I might also optimize cardiac output. And I'm showing you examples where on the first one, okay, if you optimize, on the first one, if you optimize, don't optimize correctly, what you end up doing is you end up doing a lot of using a lot of energy. And why this is bad? Because these are implanted devices, so they will run out of energy in something like 6 to 7 years. Then they have to be reimplanted. And these days, even some children have to have pacemakers. So we are talking about long-term usage. And of course, on the other end of spectrum, you have a situation where you end up in an unsafe situation, so you will be using little energy, but you might unfortunately kill the patient because the heartbeat doesn't beat often enough. Okay, so this is just a summary of the pacemaker, but there is a very interesting and unexpected benefit. What we developed for the pacemaker is the model of the heart, and that model of the heart generates ECG, synthetic ECG signals, okay? Synthetic, and it can learn from a patient. So what I have is I have an in silico version of somebody's heartbeat, okay? I mean, that's what my model does. And then I was talking to our security expert, and, at that point I knew that there was a company called NIMI, this is a company in Canada, which actually introduced ECG as a biometric identifier, ECG on its own. So you have a band, this band that you wear, and to start with, it will just record a template, which is your ECG heartbeat, and then when you go into a secure room, it will check quickly, whether it is you, okay? But of course, I can copy. I have a synthetic ECG, so I can build a synthetic ECG. The trick there was, our modeling was already done. The trick there was to work out how to inject it into the band. I didn't do it. This was done by a PhD student in Ivan Martinovic's group, and in fact involved the use of a music synthesizer. What you have to do is you have to generate a waveform, okay? So building the model, copying the signal is easy. Now what you need to do is you also need to inject it. And we were able to do it with 80% success rate, so a very high success rate of actually impersonating the user. Okay. So probabilistic modeling here is also useful for attacks. Okay, I showed you, it's useful for verification, useful for synthesis and optimization. Here it's also useful for attacks. And we have some follow-up work. Okay, you can go beyond ECG to other types of signals. So these days you are, walking with your phone, and in fact, you are just a data factory. You're a data factory. And what we were able to show is that there are ways to predict from other types of signals, okay, what your characteristic signal is. So you don't even have to have the ECG, okay, or gait or eye movement, as long as you have enough other types of signals. These all seem to be correlated. Okay. Right. But now I will move to something which I think is sort of practiced here. I've mentioned DNA computing, and I've mentioned computing in the soup, but this is not the best way to compute, because these molecules in the soup, they have to find each other, and you have to allow for this. What we need is we need a way to compute which is based more on handshaking, localized computation. So what my collaborator has been working on is how to use DNA to build tiles, fold into tiles, and you see a picture of that tile, and now on that tile I can print circuits, and he also knows how to make DNA molecules move over the circuit, and then you can direct them. You can have branching trees, you can direct them when you get to the end. You can use fluorophore to detect, whether some cancerous molecule has been identified or not. So what I'm showing you here is the design of a tile, and on the left is the process of forming. So what I have, what's called monomer. This is one very long circular DNA molecule. But that DNA molecule is chosen in such a way that you have these small staple strands. They are about 8 to 10 nucleotides, and they bind precisely into one position, and they fold, because of course they bind different sections together. They will eventually fold into that tile, and there you see the image of the tile. Right, so DNA origami was introduced by Rothemund at Caltech, and it is a new technology. It's got high potential, but it is not very well understood. Okay, so I'll just skip over this. So DNA Walker circuits, this is how you can make the DNA molecules walk. You can control the opening and the closing of the branches, and you decide that you computed to it. What we did for this is we synthesize rates for DNA Walker to guarantee a given reliability level. Okay. But a very interesting project that I was involved with was trying to understand why and how DNA folds. And for this we worked with a somewhat artificial tile. We just took 2 copies, so they are identical, but one is showing as pink, the other one is green. We took 2 copies of this circular DNA molecule, but we connected them together. You have the same staples, okay? You use the same staples. That means that each staple will now have 2 positions. 2 positions, one on the pink one, the other one on the green one, to bind to. And we showed by both using the model and experimentally that it forms into these, connected tiles. So what that involved is building a model, and this is a stochastic model. In fact, it was a continuous time Markov chain model, but we also had to use thermal energy, and this was an absolutely huge model, so we could only analyze it using Gillespie simulation. But what we did is we then combined this with experiments, where with experiments we tried to do things to the tiles to make them misform, and in particular I'm showing you an example where, say, some staples were missing or some staples were cut. But what we did is we tried to then, using the model, predict what would happen and then try to align predictions with the experiments. And that has taken 2 years, and so a modeling student and an experimental student to get to this position. But you see, even just with simulation, you can get a pretty good alignment between the observed shapes and predicted shapes. Right, but I promise that I'll get back to the challenge of autonomous driving. Okay, so this is where we are, and I'm showing you now an image of a street that's, again, from my collaborators, the Oxford Robotic Institute, but this is now a LiDAR image, and in fact, cars these days use a mixture of technologies. Some use LiDAR, some use, dashboard cameras. It varies. But in order to perceive the road and traffic signs, okay, they have to analyze these images, whatever these images are, and what they use for that is deep learning. But, okay, as we know, deep learning, we still don't know how it works, why it works, and moreover, it doesn't give you any guarantees. But if you are sitting in that car, you might want to, request that someone will guarantee that this is definitely a car, or at least that's definitely not a pedestrian. Right, so why should we worry about self-driving cars and safety of self-driving? I don't know how many of you have seen this, but this is deep learning, which is sort of making inroads everywhere, from Google Translate to Alexa. It is also being used in a self-driving context, by Waymo to recognize traffic signs, and Tesla as well, to recognize traffic signs. But unfortunately, deep learning is susceptible to so-called adversarial perturbations. So if you take an image and change that image in some very minor way so that the human would still classify it as the same, the network will then misclassify it, and sometimes in a very dangerous way. So what I'm showing you here is an example where you can just change 1 pixel to green in an image that's telling the car that this is a red traffic light. You change 1 pixel and you can do it very quickly, okay, and it's classified as green. If you're sitting in that car, I'm sure you wouldn't want that. Now, on top of that, what we were able to do, so neural networks are characterized, after training by so-called accuracy. Accuracy means that, well, you have a test set, but that test set is a finite test set. But of course, you have infinitely many possible inputs, of images. I mean, maybe not if you consider discretized images. I think in mathematical functions, you'll have infinitely many. For discretized images, you'll not have infinitely many, but you'll have an absolutely huge number of them. Okay? Now, if you see accuracy of 94.3, that's a very high accuracy, but it's computed over a finite set. okay, of finite test set. What we were able to do is for each image in that test set, we could just change up to 3 pixels and the network misclassified it. So that's what I mean. I was able to reduce it to 0% accuracy. Okay? So I think we need to do better. I can show you some more examples. So this, when I showed it at the Royal Society, I was apologizing. Well, you see manipulated images, but images manipulated by my software, and yes, you see there are just random blobs that look kind of unusual. Probably wouldn't see them on a real traffic sign. But I was told that if you go to Alaska, they shoot through traffic signs in Alaska. So then these traffic signs would look a bit like this, where you would have, and you can find them, you can look them up. I've double-checked since, so you can see traffic signs in Alaska which are shot through. But this is not just, you can have wear and tear, you can have just very small changes which are invisible to humans, but the network will dangerously misclassify it. So because of that, I started working on guarantees for deep learning. If you are in deep learning, you will have heard about MNIST, which is this handwritten digits data set. And what I'm showing you here is at the bottom examples which have a neighborhood where there is no adversarial example in that neighborhood. That means that there is no image that would throw the network into misclassifying it into something else. And at the top, they all have adversarial examples. And what I'm doing is I'm setting up 2 processes. One computes the upper bound, the other one computes the lower bound, and I want them to converge on the diameter around an input, such that in that diameter, there are no adversarial examples. So my guarantee is the network will always give me the same result in that diameter, on that neighborhood. See, this is not probabilistic, but in fact, deep learning is probabilistic because we have dependence on data, and it is Bayesian dependence on data. So what we need to do is we need to incorporate this into decision making. And this then takes me to a probabilistic formulation of the problem, where instead of computing guarantees in the sense of the non-existence of adversarial examples around an input, I'm asking very similar questions to what I've been asking before. I'm just asking, is the probability high or low of finding an adversarial example over that input? And this was presented 2 weeks ago or last week in Hawaii at the AAAI conference. Okay, so I've given you some examples of what I'm doing in the context of self-driving, but have we solved the problem? Okay, I mean, even if I keep going, working on probabilistic guarantees and, these other types of guarantees, have we solved the problem? Well, I would venture to say that no, because that problem is very, very complex. And the main issue there is that if you have self-driving cars driving on the same roads as humans, then you will need to deal with these issues. So, for example, locals in Arizona are already complaining that the self-driving cars which are being tested there, they behave too conservatively. So people get very annoyed with them. Okay, and this is just Alphabet's headquarters. So Waymo, is a Google offshoot, so it belongs to Alphabet. So their own company, headquarters are getting annoyed. Another one, what do you do? I mean, do you actually insist that self-driving cars follow the rules? or do you allow them, sometimes to go on the pavement, if there is a child, for example, on the road, so these are all very difficult issues. And that means that in addition to the technical problems that we have, what we also need to be able to deal with is these social subtleties, in the way that we communicate, with self-driving cars. I mean, we were talking about this. I mean, is it really sensible to use deep learning to do traffic sign recognition? Should we perhaps have an infrastructure which just kind of sends the signal, digital signal, a digital traffic sign to the car? We know that the in-car communication and in-between car communication is now very good, so we can build on this infrastructure. But what we also need to be able to reason about, this is what my kind of next modeling project is taking me towards, is we also want to be able to reason about trust, okay? So for issues, for example, like me, do I trust a self-driving car to take my child to school? There has to be a certain threshold, and that trust is not just for us humans. What we also need to do is need to build this kind of trust and trust reasoning inside robots, and perhaps also inside self-driving cars, because some of these decisions are moral decisions, and there are very difficult conflicts that have to be resolved. But we need accountability, just as we've learned with aircraft. The notion of a black box is crucial. What we need is to have the notion of a black box also for self-driving cars. So to finish off, I'll show you an MIT case study. Has anyone here heard about the moral machine? So you can actually find it on the website. Okay, so what this is, it's a website, and they've done now a huge study because this website spread around the world, and they have analyzed the data that they have and correlated them with sort of local histories in each country. But this is a very simple question. If you were programming this car, okay, and imagine that there is a decision in there, someone asks you, how do you make that decision? And if you continue, you kill lots of people, but if you veer off, you only kill one. Do you know how to program this car? I mean, there's no alternative. There are just these two choices, okay? So, would you know how to program? But I mean, these are machines. They already do it. It's just they make these choices at random, in a split second. I mean, humans also have to make these choices. We don't know how. So I think most people in that situation say, well, utilitarian, I'll veer off. Okay, killing one person is better than killing lots of people. That's what philosophers will tell you. But if you now have a look at the second one, okay? Well, yes, so obviously, you don't want to kill the one person. You want to veer off to the right. But what if you have a crash barrier on the right, and you are the rider? You are not the programmer, you are the rider of the car. Okay, you would then make a different decision. And then you might end up, with cars that programmers, engineers would design and develop, but nobody would want to buy because they don't want to die and they don't want their children to die. And then taking it, even further again. To what extent, at some point someone will have to make a decision. Which one is better? The person who paid for the car is riding in the car, or lots of people on the road. I mean, these are, very, very difficult decisions that they will have to be resolved somehow through regulation and, a combination of, something where we have to involve ethicists and philosophers, not just engineers. But it is something that engineers and computer scientists need to learn. Okay, so with this, I would like to finish. So I have shown you a brief overview at the high level of probabilistic modeling, verification, and synthesis. And I hope I've shown you, that it can be good for safety, performance guarantees, but also for prediction, attacks, biometric attacks, optimal synthesis, and, lots more, for example, DNA folding prediction. Okay. Right, and as a computer scientist, theoretical computer scientist, working, in these exciting fields, I think the main message, for me is that, it's great to see so many students here. These are really very exciting topics to work on. But what we mustn't forget about is knowing the limits. And this is what computability, told us. There are some things that you just can't do, and these days computer scientists know that they will not try to write a particular program. I'm not sure whether in this world we have got to that situation of being aware of the limits, for which we need rigorous foundations, we need formal verification, and we need, safety assurance. But also we need to think about implications of AI, and especially not AI, not just in self-driving, but in general in autonomous decision making. These days autonomous decision making is used in many cases. For example, whether to release someone from prison or not, and the issue of bias is already high up in the news. So they have to be considered and hopefully resolved. So there are many, many challenges, despite the progress that I can claim I have made. And I'll finish with a tribute to Robin Milner, because I was greatly influenced by him, and I was working with him on the Ubiquitous Computing Grand Challenge. Now, ubiquitous computing is actually something which was introduced by Mark Weiser in 93, okay, 93. And this talks about computing disappearing, and I have to say that I'm amazed myself, because when I was working with Robin Milner on this board about 10 years ago, I didn't think we would be able to make that progress. It has literally disappeared. I mean, who's buying desktop computers these days? You've got them in your phone, and yeah. And what Robin Milner was saying is that we have to keep a live connection between theory and application in computer science. So theory will solve problems, but you have to look at applications in order to understand which problems are the important problems that need to be solved. And I've always benefited from both sides. So, okay. Thank you. And I would like to thank my collaborators and my students for all this work. Thank you.
So thank you very much for a truly inspiring lecture. We have time for questions. I would like to ask you to ask the question in the microphone, because we are publishing the lecture online, and I want to capture the question in the microphone. So, any questions?
Yes. Yes, there was in one slide in the beginning there was deep science. What does that mean?
What does it mean, deep science? Okay, yes. I think this was on the slide where I was saying that autonomous driving is a very complex problem, and it's a problem that involves engineering. And this, by deep science, in that case, I meant not just deep computer science, theoretical, rigorous computer science, algorithmics, perhaps, AI planning. Yes, that's what I mean.
Thank you.
Other questions?
Hello, and thank you for the interesting lecture. It was very, very good. My question is, how do you feel about the information security concerning the autonomous vehicles?
That is a huge problem. That is a huge problem, and I really don't know how it can be solved. I mean, from what I know by talking to automotive companies, this is something that they didn't think of when they introduced the, because, you know, when the in-car architecture was introduced, they weren't thinking of connecting cars to the internet. This came next. And of course, as soon as you connect the car to the internet, you open the car to, you know, all the attackers and adversaries. And that is an afterthought. I think what we need to do is we really need to re-engineer, I think, that in the car. But if it is all in software, then we know that it's possible to find a loophole. There have to be, I think, there has to be a stronger protection. But, you know, it's not just for autonomous cars. I mean, you know, it's sort of coming into the news. You take any of these devices like Alexa and put them in your child's bedroom, you know. So, yeah, you know, there are already court cases, I think, going through because someone was listening, you know, to what was going inside. These are all huge problems, okay? But what we have is like a wild west of technology, which is a great progress of technology, and what we need to do is we need to stop and think about the implications and find workable solutions. And hopefully without losing too many people along the way. I mean, you might just lose a few cars, you know, but...
Thank you very much for the lecture. On this moral machine slide, we at that point that we have only two alternatives. Doesn't it mean that if we are only left with these two alternatives, it means that we made a wrong decision before that point?
Well, okay, so there are different views about this. So this moral machine is based on what is known in philosophy as the trolley problem. This is just a variant of the trolley problem, okay? Now, what I'm pointing out here is that, yes, you've reduced it to just two, but the person who's sitting in the car paid for the ride. So you have, you know, how do you then, you know, as a programmer, as a car manufacturer, decide? Because someone will have to decide, and this will probably go in the advertising, my car will not do it.
But wouldn't it be like this, that even if the human is driving and he has to make a decision, he might kill that guy?
Exactly, but humans do that, yes. And we have, you know, insurance policies for humans, but we don't have it for autonomous cars.
But if we have a machine that making a decision, there are higher chances that it would find alternative which both of the person is alive,
right.
or we could improve the sensor that can detect the guy, like.
Yes, so,
like
okay, so I can tell you that there is, yes, Ben Kuipers, who is a roboticist, he talked about this problem, not the moral machine, but the trolley problem in the context of, you know, autonomous driving, and his view is similar to yours, okay? What probably happened here is that there was a point which passed the point of no return. Okay, there was an earlier choice that that car should have made. So you're absolutely right about that. I'm giving you, an example where this didn't happen. So even if you have an earlier point, if you are familiar with safety engineering, you still have to consider that something has gone wrong with all your protections. So whatever you do, you will still get to that point. And someone will then need to resolve this.
Thank you.
And I hope not the programmer, but if you think about using deep learning, who is the programmer? You see, if you have a programmer writing code, then you can look in detail at the decisions and the logic of the decisions. If you have deep learning, learning, it will learn from patterns, and how well it learns will depend on how good the quality, the quality of the data, whether this kind of pattern has appeared in the data or not. And, optimization, yes, how good your optimization software is. And perhaps the architecture of the network, yeah.
Sure.
Going back to information security, a question: do you believe it is possible to create a system, an autonomous car system that works completely independently without any external internet connectivity, which would allow for attack vectors on the car?
Well, without internet connectivity, you just have to have an alternative communication infrastructure. Yeah, I think more or less, I think the self-driving problem in controlled situation is more or less resolved. So yes, if you ask Elon Musk, and maybe he'll build a tunnel or, some highway from I don't know, San Francisco to Berkeley, that goes over ground. Yes, I can see you don't need, yeah. But you see, that will solve your information security problem, but it would be very expensive. And I think we need trade-offs, and trade-offs are really about asking, is this good enough? It is not about asking whether this is ideal, because we have to take other things into consideration.
Thanks for your lecture. You have an extensive study about, let's say, guaranteeing the performance of deep learning networks. My field is exactly the opposite. So how to play with this, let's say, guarantee, or let's say the performance of these kind of softwares. I want to ask you that. Usually in my study we have to let's say compute, or let's say we have to see how much is our window to play with the, let's say, the performance of the software. And I want to ask that. My question is that how much is the window we can play? If we reduce the performance of the network like 2%, will it work? Is there a big difference according to your expertise or what you have?
Sorry, so are you talking about performance, meaning accuracy?
Yes.
Of the network? Okay,
yeah.
So you say your accuracy is 2%.
Yes, if it's 98%, can we reduce it to 96%? Will it make a big difference or not?
Well, that's right. That is something that we still don't understand. What you probably know, but I think people who are new to deep learning, they don't realize that all these accuracy figures, assume that the input data distribution is the same as the test data distribution. And that's the only situation where your 98% is correct. But in many cases, we just don't know. We don't even know the input data distribution. You know, you develop a car in Arizona and you want to take it to Surrey or Oxford. You don't know the input data distribution. There will be lots of corner cases, lots of patterns that no one has seen. So you see, that's why there is an issue with this reasoning. You know, it's the test you do accuracy, computation based on a finite set of data, and you've made this assumption that you've selected this test according to the input data distribution. But we don't. So that's the first thing that we have to solve. You have to guarantee that the test is selected according to the input data distribution. I don't know how to solve that. And the other, of course, will also be to do with how each layer, you know, behaves. So I didn't mention here, we are exploring Lipschitz constants, you know, to put boundaries. Yeah, you know, but that's the next problem, understanding how the maths works and whether that would give you guarantees, which I would expect. I think some of these guarantees will just be a function of the choice of layers and the choice of parameters. Just as you have in control engineering, you know, for this type of problem, you have to choose something with feedback, and that's the parameters because you have impossibility results, you know, okay? I think we would need that for deep learning. It is, you know, in fact, it goes hugely beyond what we computer scientists are familiar with. We are used to discrete maths. We are not used to continuous maths. What you do in deep learning is you even take a discretized image, okay, and convert it to 0, 1 real values. And no one's even worried about that. And we know about problems with floating point and, you know, how much damage it did to Intel. So yes, you know, I think we do need to stop and think.
So it's obviously very hard to know exactly how these models work, like deep learning models. And for that reason, I think it would be important to construct models in which we can kind of make proofs to show that these networks can learn patterns. Is it at all possible to do that? And how would we do that in that case?
I do hope that it is possible, but we need to have a lot of insight. I mean, you just think about something like, you know, computability results. I mean, there are just some problems that you wouldn't, you know, even consider as implementable. And I think we need to develop this kind of judgment, I think, about, you know, what happens right now when you have a neural network and you are asked to develop a neural network for a particular type of application. You just look at other neural networks and try to adapt it and tweak it. But I mean, there is really no theory that tells you that if you double this constant, then you are going to get better results. You do trial and error. And, you know, even the best people in machine learning just do trial and error. I mean, the Alex network for vision, I think that took 2 years of trial and error. We have to move beyond. I mean, it's impressive what you can do, okay? If you spend a lot of time engineering and looking at data, it's incredibly impressive. But this is not something that you can then sell as a technology to automotive, because automotive companies, they will then need to go and show to the authorities that they have technology, you know, that is safe. They have processes that are safe. And I wish I had the answers, but I don't.
Do you know if these situations have been tested with like real self-driving cars in like some sort of simulation environment?
So the moral machine at MIT is a website, so you can find it, and it is a questionnaire. So what they have is they give people these concrete scenarios, and then people answer them. Then they kind of have to do a check on data quality, because of course some people will try to abuse the system. But they have more recently, I think, a paper in Nature which actually shows very interesting correlations between these types of decisions and kind of the cultural traditions of the country. For example, in Confucian countries, people tend to be more utilitarian, and the human just doesn't matter, it's all for the public benefit. But in the Western countries, the behavior is different. They have these correlations already.
But what I mean about like self-driving cars themselves, so if you, instead of, they operate, they get as an input some video feed, and you just, add like a situation like this in there.
Well, so do you know what a Wizard of Oz is? Yeah, so there was a study at Stanford using a driving simulator, and this was trying to test how people sitting in these cars would behave and how they would communicate. And in that study, they discovered that, for example, humans would test these systems to the limit, and they would sometimes abuse the system. If you're sitting in a car, you would probably try. You want to go from A to B, but you would just try to test it whether it will avoid some dangerous situation. So you'll try to tell it to go to a dangerous situation first. And people do that. In real, for example, tests with pods, where the safety mechanism is if they spot someone in front of you, they would stop. People just test them. And the cars, these pods just spend most of their time stationary.
Okay, so was there one more burning question? So last question.
So much pressure.
There you go.
All right. Finally, I would also like to thank you for the interesting lecture. Personally, I'm not a computer scientist, but I feel like I still got plenty out of your lecture. So thank you for that. I guess my question is, I think the biggest problem with self-driving cars is humans, because the cars have to adapt to this environment with the pedestrians and human-driven cars. All right, okay. So I guess the question is it the right problem to try to come up with an autonomous car that can handle itself in human traffic, or should we also put more work into the transformation of infrastructure to adapt these autonomous vehicles? For example, you spoke of these traffic signals that could also transmit information wirelessly. So
that is precisely the point. I think some people, in the area are already saying, if you remove humans, then the self-driving problem is already solved. Okay, as long as people sitting in them, because no one would jump in front of them, So, but this is, I think, a choice, and I imagine that different countries would probably make different choices. I think what I've also heard is people who are working in safety critical systems. They are saying that self-driving as a concept just doesn't make sense, because the problem is just too complicated. And it's not because the technology itself is unsafe. The technology itself, if you measure it by reliability, then yes, this will be better than humans. It's again because if you put that technology alongside human-driven cars, you have problems that you didn't anticipate. But that doesn't mean we shouldn't be working on it. And in fact, what you kind of don't realize, but you know, automotive are already selling cars with self-parking, you know, autonomous braking. So all these are side effects. They improve reliability, but in contexts where we do not expect the driver to be in control of a car when the car is driving itself. This is not a reasonable expectation to put on a human. I think the cars have to be either fully autonomous or, you know, people have to be engaged. It won't work otherwise. Yeah, these are all very difficult choices, and they will have to be made somehow, I mean, not by regulators, I mean, not by us scientists.
Okay, let's wrap this up here. Thank you very much for coming and contributing to this lively discussion. And let's thank once again Professor Kwiatkowska for taking the time to come to Turku and to give such an interesting lecture. Thank you.